Okay, thank you so much, and such a pleasure to be here with you. And I was just listening a moment ago to Richard's beautiful talk about the multiverses, and so he's right. We can create artificial materials which create their own set of fundamental constants, if you like, or at least they modulate constants which appear to be of a particular nature in the abstract, but in a particular material have their own manifestations. So if you like, some of what I'm going to be talking about is trying to make a different multiverse where we take a semiconductor inorganic material and make it behave in some ways like a molecular system. And that's through making what we will call a quantum dot. And another thing that Richard said that was kind of interesting is, at the start of many good projects is somebody telling you that it cannot be done. So it's certainly the case for me that when I was a postdoc at Bell Labs, there was a lot of work going on studying really, really pristine, very high quality films of semiconductors that showed beautiful quantum phenomena. And fabricating them was very complex and advanced. And I was in a corner with my mentor, Louis Bruce, and some other colleagues, a small group, and we had this thought that we would be able to make in a little flask, again, a little bit like what Jean-Marie was saying, to try to grow at low temperature in a flask what had previously been grown as a very complex patterning. And so the first time that we made some quantum dots that showed a quantum size effect, I was so excited. I'll show you. I went to talk to one of the top theoretical physicists at the lab at the time and said, "Look, we see this quantum size effect." And he looked at the data that I had, and I was very early in my career, and so he kind of looked at it and looked at me and went back and forth like that. And I could tell, I mean, he didn't want to be mean, but he looked at me and he said, "Paul, you seem like such a nice young man. I really think you probably should work on something else." and the reason was because he really believed at that time that it would not be possible in a liquid flask at low temperature to make the kind of quality of material that was being made all the time in these very advanced systems. So I'm going to tell you about a story in which we are making a kind of material, and then, here's a funny thing for you to contemplate at the beginning. I know you're here because you're interested in sustainability and energy. And in this case, really, I'm interested in this material that I fell in love with. So for me, I care about sustainability just like you. But one of the traps for me is that I could fall in love with my quantum dot and think that it will have a use in energy that it really doesn't. So my job then is to be careful and to find if my material can really have a use, to find it carefully, and to be honest with myself about where it might fail, even though I'd like it to succeed. And that kind of interaction is a difficult one that every scientist at some point in their career has to go through. So in my case, I believe that there's going to be a kind of new application of these based on their light emission, but not on their charge separation. So we'll see that as we go along. So, as I mentioned to you at the beginning, there were folks at Bell Laboratories studying very, very, very thin semiconductors, because in those materials they could change the electronic behavior of what was a normal solid. And we were thinking in our efforts about a different idea. Let's take a piece of solid and we'll break it up into tiny crystals, which are small on all three sides, just really tiny ones. And so imagine now taking a solid and breaking it in two, and then again and again repeating that until the little fragments become extremely tiny. Then, of course, what I will see is that there are scaling laws. In other words, every time I make the material half the size, its properties will change in some fundamental way. And perhaps the most famous or simplest scaling law that one can understand immediately is the one for melting. Now, the reason that I started studying these was because this person told me at the beginning, you cannot make good quality material. And after I got over having my heart broken and thinking that I had to go work on something else, I began to think, well, what if this guy's wrong? What if he turns out that actually there is a way to make it, and what if there is? Who knows? And so for that, I had to go back to studying the fundamental properties of the thermodynamics of the materials that I was looking at. And I had to ask, what are the properties? And so one of the fundamental properties of any material that is a solid is its melting temperature. So here you can see the melting temperature of a small crystal as it gets tinier and tinier. And what you see is that if many of the atoms are on the surface, because every atom bonds to every other, the total binding energy is reduced, and the melting temperature becomes smaller, roughly like the ratio of the surface to volume. It's a bit as if everybody's holding arms together, and if there's only a few of you, it's easier to pull apart than if there's a great large number. And so that, of course, dictates the reduction in the melting temperature. Why is that important? Well, that's because that then means that I can grow, in principle, this material hundreds of degrees lower in temperature than where those other materials were being formed. That means potentially inside a hot liquid instead of in a higher temperature vacuum system. A second scaling law that you will relate to at some point, possibly even now, but many of you have probably not yet made that fateful or important trip in life to the jewelry store where you try to buy a diamond ring. But at some point, you may do that. And when you do that, you'll find that when you look at the diamonds, you're pretty quickly forced to choose a particular size because there's a scaling law. And the scaling law is right there on the De Beers website where it says, big diamonds are rarer, so a diamond of double the weight costs 4 times as much. Why is that? Well, because if there is a defect in the diamond, it won't look right. And you want that defect to go away over time. If the crystal starts to grow and there's a mistake in it, you want that mistake to slowly leave, and that takes geological time because the diamond is big. And so that's why the bigger the diamond and the more perfect you want it, the longer it takes for it to anneal out. It turns out that what we're studying now takes that problem and turns it upside down. So instead of wanting to have a really big crystal that's perfect, I can have a really tiny one. And for a tiny one, the time for a defect to anneal out should be very short. So if I combine the finite size and the temperature, it should be possible to make a really perfect tiny crystal. That doesn't mean you will always make a perfect tiny crystal. You have to actually do it right. But it is possible to make crystals where only one out of many millions will have any defect in them at all. So you can make highly, highly perfect tiny crystals. And indeed, for many years, we studied those kinds of behaviors, and we could find it out in phase transitions and other things that these crystals were very close to perfect. In fact, that's one reason they may show up to some degree in battery materials, because the large volume change in a tiny crystal can be tolerated. In fact, today, it's really interesting, many years later, a couple of decades later, we can actually image nanocrystals in real time and see all the atoms. And so what you'll see on the left there is a growth experiment of nanocrystals in a liquid cell. So we now have a little pocket of graphene with some liquid in it. And inside there, the crystals are growing, and we can see them. We don't just grow them anymore, but we watch them as they grow. And you'll notice 2 crystals towards the right there. Just in a moment now, we will see they're going to just find each other, and they're going to join together. And you'll see that they kind of fuse. And so, yeah, is it here? Somewhere along here is what should happen. These kind of little crystals, they periodically will fuse and find each other and grow. And you'll see that as they do that, they kind of anneal out their defects. It's a fun thing. Let's just go backwards here and find it. No? Am I missing it? Anyway, you'll see a lot of these little fusion events, like right here. There it is. See, these 2 find each other, and they fuse, and then if you look a little while later, they kind of things zoop around, and suddenly it's a nearly perfect crystal. On the right there, you see some very current experiments where we take 2 crystals and we join them together, and we can actually see how long does it take for a defect to anneal out. We can do that as a function of the size. We can connect them with different orientations, and we can measure how long it takes. And indeed, there are scaling laws for that look very much like the ones that you would expect. In other words, it scales exponentially with volume and things like that. The upshot of all this is that the gentleman who told me that we could not succeed was in fact entirely wrong. And tiny crystals can be made highly, highly perfect. And in fact, we can make them on the ton scale, which we do today. We make them on absolutely scale of many, many tons. And on average, each crystal is of the highest quality that you can make. So that's a kind of a fun thing. So what we've seen here is a little bit about the structure of a material, but what we care about, of course, is its function. What are we going to use it for? And for that, we're going to look at some other scaling laws. Richard mentioned to you this notion that if we have an inorganic semiconductor, typically two charges, an electron and a hole, just like an electron and a proton, say, in vacuum, they're going to feel each other and bind very strongly, the Coulomb attraction. But if it's in a medium that has a very, very high dielectric constant, that means it's a medium where the electric field isn't as felt as strongly by each other. That weakens their interaction. So that's true of these inorganic materials. They have a weak Coulomb interaction because the atoms they're made out of are so polarizable, the electric field doesn't connect them very strongly. So how can we make them still feel each other? Well, one way to do that is to make them be in the same volume so they can't get away from each other. Just make the volume very, very tiny. And it turns out, one of the things you'll learn when you study quantum mechanics is that if you have an electron, for example, it actually has a kinetic energy. It moves very fast. And if you push it into a smaller volume, its kinetic energy will increase. It will move even faster. And that's what happens inside one of these tiny crystals, is if we push the electron and the hole into a tiny, tiny volume, a smaller one than they would like to occupy normally, they start to move very, very fast, and their band gap increases, and the color of light that they absorb and they emit changes from what would normally be there. And that's called quantum confinement, or the quantum size effect. And it's related in its essence to going from a continuous material to a tiny atomic or molecular one. And it means that we can tune the energy levels as a function of the size of the crystal. We're going to use that. We're going to make many different colors that way. Now, there's one thing that we have to be aware of. I take this solid and I make it very, very, very tiny. And there's an electron and a hole running around inside there. And what they will do is they'll also push out. They're trying to get out. And that means that they'll sample the edge of the crystal. And that edge of the crystal has what I call wild things. What that means is simply they have little spots on the surface where there are energy levels that are low and where a charge could just get trapped and localized. So what I need to do in order to really make a great barrier, a box for an electron in a hole, is I have to surround this semiconductor with another material of a larger band gap, and that then will lock the electron and the hole in to be very tightly controlled. Once that had been done, it actually became possible to take these crystals and use them as if they were macromolecules. They're about the size of a protein. So some years ago, we were able to show with my good friend Shimon Weiss that we could use these as biological labels. And what you can see up there in the upper left is an image of the absorption and emission of a dye molecule versus one of these quantum dots. And there are some differences which I'd like to point out to you. Of course, we can make many different colors by simply changing the sizes of the crystal. That's the quantum size effect. So that's the scaling law. But these particles have very narrow emission spectra, and as I'll show you in a moment, that's really related to how much of volume the charge occupies inside these tiny crystals. Here's a labeling of a cell with a dye molecule and with a quantum dot. And what you can see is that the dye molecule will bleach. It eventually photochemically degrades where the quantum dot does not. Why is that? Well, in this molecule, the electron that's excited, it's into an excited state, a photon has come in or some other excitation has come in, and so there's an electron rattling around in here. Now, this very beautiful molecule, if there happens to be a localization event at any little spot here, there's a possibility of a chemical reaction. And the probability that that will happen is related to just how big this thing is. This little crystal is about 100 times or 1,000 times larger. So the probability that an excitation will localize on the surface, as long as I've built that shell well, is really tiny. And that's why this crystal will be more photostable, because it isn't as easily reactive. Furthermore, because that electron and hole are delocalized, the amount to which they make the local bonds change, their length, is reduced compared to here. And as a consequence, they have a narrower emission spectrum. They're just not as strongly coupled to the vibrations of the material. So it turns out that that made good biological labels. We can take those quantum dots and we can put them into a cell and label it, and that is a commercial technology that can be used for biolabeling. It has some advantages and some disadvantages, but it is used by thousands of research groups every year. Now, the next question would be, could we use these in a display? And the answer is yes, they can be. One of the simplest ways of doing that is to make a film out of these particles. So you take two sizes, a green and a red emitter, and you put them into a plastic film, you cast the film, and then you put it inside where a normal LCD panel would go. It just goes. It's a drop-in kind of technology, if you like, that goes right inside there. And so now you'll get your red and your green colors from a quantum dot. And indeed, those now make some commercial displays, and you can go and buy a television. And yes, the prices did start out high, although they've been coming down quite a bit recently because the volume's going up. And so, recently I was in Hong Kong, and most of you probably haven't been there, but one day you'll probably go. And so Kowloon, there's this giant bay, and on one side is the major part of Hong Kong, and on the other side there's this beautiful boardwalk in Kowloon across which you can see the city. And so there's the city, and I'm walking along, and there it is, SUHD Quantum Dot TV. And I'm thinking, oh, that's really nice. I'm walking there along with my wife, Nicole, who often reminds me that the world is more complicated than I think it is, and so which is very helpful. And so, she pointed out to me that if I just looked a little bit more carefully over here, I would see right next to it is the OLED TV. And so there you are, Richard. We're on the same boardwalk there. And so now you start to think, what's going to happen? We're in a little bit of a competition there. Is it OLEDs? Is it quantum dots? And so then, it's time to go take a little break. And so for me, I go out into the garden, and I take some photographs, and I take some deep breaths, a little bit of imaging of things. And so here you can see this kind of flower, and you see this combination of colors there in the flower. And then here's another one. And this flower also seems to have that same combination of colors. And if I go and look at a color wheel, I see, oh my gosh, those are complementary colors to each other. Nature is actually doing some very interesting things with our eyes, which makes us look at things in certain ways. That, of course, attracts the bees that it needs to attract. So it's very important to represent color well inside this world. And actually, our eyes have in them red, green, and blue detectors. And if I look carefully, and these are the wavelengths at which those detectors actually work. So if I want to represent everything that a human eye can see, I need to have emitters at these kind of corner wavelengths. And here is these pluses that you see everywhere here. This is a gentleman who went around with a colorimeter inside a kind of office space and just went around looking at every single color that was in the office space, right? And this is the color space that was occupied by that. And this is sort of a conventional display that might be like the one that this thing is showing here. It shows this range of colors, so it's missing all of these colors that our eye can really see. In fact, it's also missing all of these. And so the quantum dots actually have the ability to fill out these triangles. In fact, we can make a display today that really fits all three of these corners quite well. It's just slowly the marketplace is developing towards it. So over time, quantum dots will do well because they have a narrow emission spectrum. So if you want to get full power out of it with a low battery cost in a display, but represent all the colors, the quantum dots will do very well for that because they can, in fact, represent all of those colors. And so that's an evolving story. Now, I'm going to switch topics. There's lots of other things happening in quantum dots that are lots of fun, but I'm now going to switch to the energy topic. And what I'm going to talk with you about is what would happen if we made the best possible core shell quantum dot. And the idea that I'm going to present to you is one that's developed over a long period of time after lots of mistakes. So it's an understanding that has developed over a period of time. And it's going to be about really a nearly perfect quantum dot, which we maybe can or cannot make. We don't know yet, so we're going to find out. And here's the idea. Imagine that I have a film of plastic that has quantum dots in it, just like that display one, except these are special quantum dots where their quantum yield is essentially 100%. Every time they absorb a high energy photon, they convert it to a red photon. And we'll have the sun incident on it. And oh, by the way, what's interesting is that even if it's a cloudy day, the cloudy light will scatter into this array. And if I have a very, very special mirror on, which Harry Atwater and friends who are going to help us to create, a very, very special mirror here that will pass blue and green light, but will reflect red light perfectly. So if I have that, exactly passes blue and green light, but reflects red light, then I can take all of the energy from the sun that's in the red and green and convert it to red light. Now you say, well, who cares? So let's imagine that I'm trying to make a lens, okay? So I want to take light and I want to focus it tightly. Why would I want to do that? Well, you'll see that in solar cells, there's many reasons to want to do that. I'm going to describe that to you in a minute. But just imagine, for example, that I want to make a good lens. And what I'm going to argue to you is that the special quantum dot can focus light better than any geometric lens could ever do. In principle, better. Why? Well, you're seeing this red dot here from my laser pointer, from this laser pointer hitting the screen. The screen is white particles, so it scatters light at you. So every red photon that you're seeing with your eye is coming at a different angle from the screen. So they're all coming from one angle from this pointer, but they're all at different angles pointing at you, right? So imagine now that I said I want you to make a special optic that will take all those red photons and reverse them so they come from your eyes and they all come right back into my laser pointer. Some people are giggling for different reasons, who knows? But one reason could be because you recognize the inherent futility of wanting to have all of these photons come back into this laser pointer. You just can't get that to happen. It's against one of the laws of thermodynamics. Entropy says that you cannot do that. So how could I do it anyway if I still wanted to? Well, the way that I could do it would be to take high energy photons, blue ones, and inside this material convert them to red ones. Then the energy difference that I've paid there could be used to organize the photons so that they would all go backwards. And that's essentially what happens inside a luminescent concentrator. I take some high energy photons and I convert them to lower energy ones, and the energy difference can be used to focus the light down tighter than it would normally focus. And the greater the shift between the high and low energy photons, the tighter I can focus the light. So in principle, if I have a 300 millivolt energy separation, I can exceed the quality of even the most ideal lens. Now, when we started this work, the best luminescent concentrator, as these are called, that had ever been made, had an efficiency of around 10. And there are various reasons for why that was true, but they mostly had to do with the fact that they were made out of certain kinds of molecules where you couldn't really get the narrowness of the spectrum because of the intrinsic coupling to vibrations. So in the few years that we've been working on this with our friends, with Ralph Nuzzo at Illinois and with Harry from Caltech, we've been able to take this and go well over, we've now got some that are over 100, and we may be able to go further in the concentration factor. Now that's still not as good as a lens, but we're still very early days in developing this kind of thing, and so that's where we're at. Now, how can you do this? One more thing about why you might do it. Some of you may have seen occasionally when we make a solar cell, one way to have them is just to have a simple panel, but another one is to concentrate the light. And the reason that you concentrate the light down is because when that light is very concentrated inside the semiconductor, it actually changes the energy levels of the semiconductor itself. You make so many electrons and holes that it changes the energy levels of the semiconductor and it increases the operating voltage. So if I convert the light from red and green to red and blue to red, I lose some energy doing that. But if I get a concentration factor over about 500, then I get most of that energy back later as operating voltage of the solar cell. So how would this work then? In principle, what I want to do is have a quantum dot where I have a large absorbing material in the shell and a tiny core that all that energy falls into and has a really, really large quantum yield, as close to unity as possible. And it turns out that it's incredibly sensitive to this. In other words, if the probability that when a photon gets absorbed, that it then gets emitted, a red one gets emitted, if that probability is 99%, I can only get to a concentration factor of 20. But if it's 99.9999%, then I can easily go well over 500. And it's not just the quantum dot that has to be good, it's the reflectivity as well. So I have to make really good optics, not kind of good, really good. And I have to have not just a kind of good quantum dot, but a really good quantum dot. So the question is, can we do that or not? Well, in the short term, if we can just get to a couple of hundred or so concentration factor, it turns out we can take our material and place it potentially onto a silicon cell. And I think Harry may even discuss some of this tomorrow. So there could be some near-term application. But the bottom line is this will only become really, really useful if we can get a really, really high quantum yield. Well, can we make a really, really good quantum yield or not? It turns out that the materials that we make today have a quantum yield that's so good that nobody knows. It turns out that nobody knows because if we try to measure it in a conventional way, you end up taking your material, you put it inside what's called an integrating sphere, you measure how many photons come in, and you try to see how much energy is put out. And you try to compare those two. That will work to about a 1%. If you work really hard, maybe 0.6% or something. We need to go to many nines. So here's an experiment we've been doing with our friend Alberto Soleo and with David Hanifi at Stanford. It's one approach in which we simply measure the heat. In other words, we have a blank cell that a laser beam goes through, and then another one that has our quantum dots inside, and we measure the temperature difference between these. And we do that as we change the photon energy. And a simple way that you could imagine this is if I have the energy of the excitation exactly at the band gap of the semiconductor, of the quantum dot, exactly at the band gap, and if the quantum yield's 100%, there'll be no heat. And if I go a little bit higher, a tiny bit of heat, a little bit of extra photon energy, a tiny bit of heat will be created, and so on. So if I measure the amount of heat as a function of the energy of the incident light, I can back out from that the degree to which I have a high quantum yield or a low one by measuring the heat, in other words, an affirmative measurement, instead of trying to just look for all of those photons. And what's so interesting about that is that in this particular kind of quantum dot where we have a large shell and a tiny core of these two materials, the shell is enormously larger in volume than the core, and yet we can excite anywhere inside the shell and all the energy will fall in, and it comes out with a quantum yield that's to within the accuracy of this technique, 0.997%, although it's not clear yet what the accuracy of this technique is. And it's not clear yet that that doesn't mean, because there's some error in it, which we're still trying to figure out. It's not clear whether we haven't already made a quantum dot that's got a good enough quantum yield, in other words, 4 or 5 nines, and there's going to have to be yet more efforts to try to measure it better. Now, I hope you remember that I had mentioned to you earlier structure and function. Right? We talked about that when we did the scaling laws. And I said, well, early days we studied the structure of our materials, the melting temperature, phase transitions, where the atoms are. And then we could move on to their function, their use. Well, now our function has said, I need to have a particular structure in which there are no defects. I have to look at that interface between the core and the shell and make sure there's no mistake. There can't be a single atom out of place. Well, earlier Richard showed you a beautiful picture of a photosynthetic protein, a photosynthetic antenna. And nature goes through and makes an atom at a time a perfect material with thousands of atoms in it. But it turns out when people make things, they are not yet able to make things where every atom is in the place where we want it to be. We don't know how to do that yet. And so here's a good challenge, because we know that if we could make, it's a simple material, it's only got 2 kinds of atoms in it, well, 3, okay, it's only got 3 kinds of atoms in it, and I just have to place them in the right spots. So it's a good place to practice trying to make something with, say, 5,000 atoms, but where they're all in the right place, no mistakes. But I'm missing something if I want to do that. I can't just have, I made the stuff and I looked at the property, in other words, the quantum yield with Alberto's new technique. I have to have a third thing. I have to be able to record the positions of the atoms. And no one can do that quite yet for a material like this, because if I have a protein, I can crystallize them, I can make them all identical, and then I can get the structure. But since these two, no two are necessarily absolutely identical, I have to look at each one to know its structure. So a few years ago, we have published some early work in which we take a single crystal and we place it again in that graphene liquid cell, if you remember. It's got a little particle inside, and the particle sits there rotating, and we measure its diffraction pattern as it rotates, and that allows us to go and make a map of all the atoms. Okay, so why don't we just go do that? Well, there are some problems. It turns out that the atoms scatter a lot in these materials, and if an electron scatters twice as it comes out of here, I can't invert that problem anymore and get the structure. So these are a little bit too big for this technique. Here's another method that we've been developing for a while. We can simply take an existing crystal and we can etch it. And this, for example, follows the trajectory of one crystal as it etches, and it shows how the boundaries of the crystal change as a function of the time when the etching is being done. So I start with a big crystal. So if I do this and I pass through the core and the shell, it turns out I think we will be able to figure out a tremendous amount about what's happening at the shell and the core. And so it's a kind of hybrid version of these two techniques. And that's something that we're working on very hard right now, which would allow us then to have some picture about what that interface looks like, and then to go back and compare that. Okay, so I mentioned that this research kind of has gone from step to step to step. I mean, first we were making a material, and then we realized, oh, if we made this material really good, it might have this interesting property that it would really be useful in a kind of solar energy. A weird kind, but a kind. And then it also was the case that we needed to have a great mirror. It wasn't enough just to have the quantum dot. We needed to have the mirror too. So let's stop and think for a moment about what we're doing. We take all these photons and we make them all go to one place. What is that like? I don't know if you've ever thought about an engine, but what happens in an engine is you compress a gas, then you make it hot, and it expands, right? So there's a compressor, there's a compression and an expansion. And what's being compressed and expanded is a gas. Well, what did we do with the photons? When we said I concentrated the photons, I took photons and I compressed them. Okay? I compressed them, in this case, in their entropy, in their angles, but I've compressed them, so I made a compressor. So what if I think about that, and I start to imagine taking all the devices that work based on gases expanding and contracting, and try to make photon analogs. In other words, I'll replace the gas with photons. Okay, so imagine, first of all, that I've got a rocket. What happens in a rocket? That's the simplest version of propulsion. I make an explosion, the gas flies out the back, and the rocket goes, right? I mean, that's Newton's laws in action. All good. Well, what happens if instead of doing that with a gas, we were doing that with photons? Well, now you're talking about a light sail. People have been thinking about light sails a lot recently. What's the idea of a light sail? I've got a material which reflects beautifully. And then attached to it, I put a little transmitter. And now a laser beam from Earth comes and hits this thing with so much power that it is accelerated to very close to a quarter of the speed of light. That's the Breakthrough Starshot project. Well, what would happen if you did that is that sail would start to move really fast, and it's actually, if it's going at that speed, in the lifetime of a human being, it could go to another solar system. Why is that a good idea? I mean, what's the principle behind this? The idea is that all the heavy fuel stays on the Earth, and it's the massless photons that are carrying the energy to the spacecraft, so it removes the burden of having to have the fuel up in space. Okay, that requires a reflectivity of, say, about 8 or 9 nines on that mirror. It also has to have an incredibly low mass and a whole bunch of other things. Harry is actually one of the world's experts on this. So you can see now that if we start to make materials which are at the limits of reflection and emission, and we pair them together, there could be some really crazy stuff that happens. Imagine another kind of thing, an electric refrigerator. So instead of a refrigerator that works based on gases going expanding and contracting like in a conventional refrigerator, imagine that you have a light-emitting diode. Maybe it would be Richard's OLED, okay? But this will be a really efficient OLED, and you know that if I want to get light out of an OLED, I have to make the voltage a little bit, I have to place a voltage across it. I apply a bias, I put some energy in, and photons start to come out. Well, imagine that I take that OLED, and now this is what has been taught to me by my colleague Eli Jablonovich at Berkeley and by Shan-Hui Fan at Stanford. Imagine now that I have an LED, but I make the voltage just a little bit too low. But it's sitting there at room temperature, so there's thermal excitations, there's phonons. So every so often, it will in fact emit light because it got the energy from the environment, and then that can come and hit a really efficient solar cell, and you can go around and around like this, and this one will get colder, and this one will get warmer, and you'll have made a little device that can be the basis of a refrigerator. This side gets cold, this guy gets warm, and you can use this to cool something or to heat something. So that's a photon refrigerator where the working gas, again, is the photons. Okay, let's go crazy now. As if we haven't. I thought this was really important to do. You know why I thought this was important to do was because I've been to a number of these wonderful sustainability conferences, and what Richard said happens. I mean, people talk about the existing technologies and how they're going to get better. And that's great, and maybe none of these ideas will ever come to fruition, but I think one thing that you should know when you're setting out in the beginning of a career is that so much is not known. When I think about when I was a student in your stage of career, Steve Chu had not yet shown that atoms could be cooled. Okay? And they can be. It was new physics. You're in the generation where people just detected gravity waves, okay? I mean, it's just, so many new things can still be found. So this is crazy, but here's a battery, and it's based on electrons being transferred at electrodes and storing energy and so on. What could we go crazy? Could we make what you would call a photon suitcase? Imagine that we had this concentrator working really well. So, blue, green, yellow photons all come into this box, and it's a box that's now completely sealed for red photons. Turns out that they're going to hit the mirrors, if the box is any plausible size, so many times that even 7 or 8 nines on the mirrors isn't enough. But if I put in really high quantum yield quantum dots, I can kind of slow them down, reduce the number of collisions with the wall. And if you work out some numbers, and if both of these are favorable to you, imagine that you've got that. So some photons come in here for a while, and you've just got them circulating inside there. So now you have photons, their energy, trapped inside this box, and then suddenly you have one spot on the wall where you can open it up, and the photons can come back out. It turned out all the photons would go out right away, and you would release a lot of energy in a very, very short time, which is something that a battery has a hard time doing. In fact, you could beat combustion and release more energy per unit time than many other kind of techniques. So you could make a very high peak power kind of battery. Will that ever happen? I don't know. Hard to say. But it's the kind of thing that one should be thinking about if you're really trying to think about what might be possible, because not everything that's possible is yet known. And one thing that we do know is that our ability to make materials is achieving slowly, a higher degree of atomic precision for larger and larger numbers of atoms. And we know that's possible to do because nature does it all the time. And so it's something for us to try to learn and emulate from. And as we do that, I think that we do have a possibility of making new kinds of energy conversion systems. So thank you for your attention.